Hi, and welcome to this fifth devlog of Orbis Multiplex, a complex, simulation-oriented 4X indie strategy game on planetary scale. In this video, I'll show and briefly describe a Fauna model which I recently added to the project. I'll also mention some stuff about the GPU implementation of that model. As mentioned in the previous devlog, terrestrial ecosystems can be simplified into two main categories: the flora or vegetation and the fauna. The flora simulation has already been implemented, so let's deal with the fauna. The fauna can be further divided into herbivores and carnivores. The two categories, herbivore and carnivore, also often called prey and predator, can be simulated using similar equations as for the vegetation, namely logistic growth functions. The derivative of a standard logistic growth function looks something like this: n being the population, r a growth parameter, k a carry capacity, and dt a time step used in the computations. If we look at some variation in the parameters, it looks like this. The r parameter determines how fast saturation is reached, and the k parameter determines the saturation level. If we look at the two other examples, where one parameter is low and the other high, we get these two curves. In the case that r is high, we call it r-selected. In the case that k is high, we call it k-selected. In nature, animals tend to exist on a spectrum between r and k-selected. R-selected species are characterized by fast growth, early sexual maturity, many offspring, and short lifespans. Most insects fall into this category, but also mammals like mice and rabbits. On the other hand, k-selected species are characterized by slow growth, late sexual maturity, few offspring, and long lifespans. Examples would be elephants, blue whales, but also humans. The R/K selection theory also holds for plants. Dandelions are an example of R-selected plants. They boom in the spring, reproduce quickly, and then vanishes until next year. Oak and pine, on the other hand, are K-selected. They grow extremely slowly, but once fully mature, they can live for centuries and come to dominate their ecological niches. Whether animal or plant, K-selected species are more vulnerable to disturbance, like hunting or logging. Now back to the equations. I use logistic functions to model both the prey and the predators. The carry capacity of the prey is determined by the available vegetation to eat, whilst the predator's carry capacity is determined by the available prey to eat. Note that the prey equation has a predation term included, p. This term makes the prey population decrease as the predators hunt. The p function models how easy it is for predators to find and catch prey. There are many ways to model this, but I've done it using a rather simple function. Plotting the function, it looks like this. Here, a equals 1 and n is the amount of prey. As the amount of prey increases, it gets easier for the predators to catch a prey. The b parameter determines how this curve changes with an increasing prey population. Stuff like predator avoidance, camouflage, and herd projection could be modeled using this p function. With the predation term included, the full prey dynamics looks like this. Here are some examples of dynamics achieved with different settings. To model my ecosystem, I use 5 kinds of animals, 4 herbivores and 1 carnivore. The 5 vegetation types are the same discussed in the last devlog. Grazers eat grass, and an example would be the bison. Megagrazers eat grass and shrub. A living example would be the African elephant, whilst mammoth would be an extinct example. Browsers eat shrubs and small trees. An example would be the deer. Megabrowsers eat all kinds of trees. Most megabrowser species are extinct today. When creating this model, I had the megatherium in mind, a megasloth which lived during the Pleistocene. A living megabrowser today would be the giraffe. And of course, I have a carnivore, which eat the 4 other animals. In my model, the megafauna are heavily K-selected, which means they can dominate landscape in the long term if left undisturbed, but are vulnerable to hunting. The normal fauna isn't really R-selected, but more so than the megafauna. I'll now go over the implementation very briefly. The planet consists of roughly 1 million triangles. For each of these triangles, I want to run the calculations mentioned previously. Since all triangles are independent of one another, this can be done in parallel. Which brings us to the GPU, the mother of all parallel computations. Transferring data between the RAM and VRAM is costly. Luckily, I only need to do it at the beginning and end of the simulation. In between, all the calculations are performed on the GPU, which is very cheap and fast. My initial CPU implementation took between 5 and 10 minutes. The same simulation now takes between 10 and 20 seconds. Migration is also simulated on the GPU. Each triangle I has 3 neighbors, J, K, and L. For each of these neighbors, I calculate the difference in food and use that as weights for a diffusion simulation. Now let's look at some results. Because of some blue screen problems, the erosion code isn't operational at the moment, but ecosystem simulation works just fine. The column map used here shows the amount of animal biomass. It goes from white to yellow to brown to black. In this scenario, animal biomass tends to be focused in large forests and on grass plains. The large biomass in forests is a result of large mega-browser populations. The grass plains are interesting since they often exhibit cyclic behaviors. In my model, grass gets destroyed much more easily than trees by herbivores. This causes waves of moving herds.
They do move in herds.
Carnivores tend to counteract these wave mechanics. If the carnivores are disabled, large wave patterns like these can emerge. This model isn't the most realistic model in some sense. Browsers don't actually eat whole trees. They eat shoots, fruit, leaves, and the occasional twig. To simulate browser dynamics more accurately, one idea would be to introduce a food buffer. This buffer would be generated by trees and shrubs and consumed by the browsers. In that scenario, browsers wouldn't consume the trees themselves, only the buffer. But for the moment, this model will do just fine. In the end, I think it's more interesting to generate interesting game mechanics than to simulate terrestrial ecosystems to 100% accuracy. And from a gameplay perspective, I think the system will be interesting. Depending on where you live on the planet, the hunting potential might vary over the year as herds migrate, or it might be more constant if you have access to vast woodlands. The dynamics might also change throughout the game. As the player hunts, the megafauna, or even the normal fauna, might go extinct, leading to uncontrolled vegetation growth, which might be a good or bad thing. The system got potential, and will be interesting to see how it interacts with player input when I get to that stage. In the next devlog video, I'll give the erosion model an overhaul, adding more interesting initial noise and the GPU implementation of the erosion model. With this, I'd like to end this devlog. As always, the project can be found on itch.io, where a free copy of the game, at its current stage, can be downloaded. Thanks for watching.